Welcome everyone. For today's prep, we're going to start to look at the alternating series test. So before we actually get to the statement of the test, let's actually look at just some examples of alternating series. And, well, the name's pretty descriptive. An alternating series is a series that alternates between positive and negative terms. And we've seen these types of lists before. Usually the way you accomplish this alternating positive, negative pattern is with this -1 raised to a power term. Doesn't necessarily have to be n-1, could be other stuff, but normally an alternating series will have something that looks like this. There's other ways to accomplish this, but this is the most common. And as an example, or a couple examples, -1 over n, or -1 raised to the power n divided by n, doing the series here. And if you write out the first few terms, which we've done here, you see the first term is negative, the second term is positive, negative, positive, negative, positive, so on. So it's alternating, it has that alternating pattern. And same thing, -1 raised to the n-1 over n squared, starts off positive, then goes to negative, then goes to positive, and so on in our list. All right, so what we're trying to do is, again, when we're doing a series, we're trying to figure out, does this infinite sum, does it actually make sense? Can we actually do that infinite summation? And what we're going to see is we can use this alternating series test to help us answer that question. So let's read through the test. So if we have an alternating series, and we have the format here, sigma n equals 1 to infinity. And the way this test is written, it's written with this alternating component, -1 raised to the n-1. Again, it doesn't have to be that necessarily. There's other ways to do this. But we normally see some kind of alternating component there. And the idea with this test is we're going to be investigating not so much the alternating piece, we're going to separate off everything else. And we're going to be investigating that. All right, so first of all that other stuff, those terms have to be positive. So we can't have some negatives there, because then it might disrupt the alternating behavior of what looks like an alternating series. So we have our alternating piece, and then this term has to be positive. And the things we check are this sequence Bn has to be decreasing. So Bn plus 1 has to be less than or equal to Bn for all n. And the limit of Bn as n goes to infinity also has to be 0. So these aren't equivalent statements here. You could have a sequence of terms, or you could have a function that kind of oscillates back and forth. Still the limit is 0, but it doesn't satisfy this. So having the limit approach 0 does not necessarily mean you have a decreasing sequence. You could have this kind of decaying oscillation or something like that. All right, so if both of these conditions then are satisfied, we can claim the alternating series is convergent. So what steps are we going to take to actually prove this, or to actually perform our alternating series? So step 1 will be to state Bn and the positivity condition. So first of all, you want to figure out what the Bn term is in your series, and just make sure it's actually positive, and state that it's actually positive. 2, the second thing we'll do is we're going to actually calculate the limit first. So then we calculate the limit. Usually it's a little easier to calculate the limit. And sometimes this test goes wrong, and it goes wrong because this limit doesn't equal 0. And we'll get to that. So first, Second, you want to show the limit. Then you prove the inequality. So you don't want to, a lot of times you don't want to go through all the work of proving the inequality and then to find out that the limit doesn't work out. So usually it's helpful, do the limit first, then prove the inequality, and then as usual, last step, actually state the conclusion. So figure out if this is going to be convergent, and then state the name of the test that you're using. So, if you're using alternating series test, say alternating series test, or you can abbreviate AST if you want. All right, so these are the steps we're going to do. We've looked at a few examples of what alternating series look like. Just a couple other comments. It doesn't necessarily have to be this -1 raised to the n-1 term. This test works equally good for other powers of -1. So some other common examples, you might see -1 raised to the n, or -1 raised to the n+1. The alternating series test works just fine for those terms. And then also, we can relax this condition on Bn. So that inequality doesn't necessarily have to be satisfied for every single n value. It just has to be satisfied eventually. So if we go far enough out in our list, we do have to be able to get to a point when then from then on, the inequality is satisfied for all n. So sometimes there might be a few terms at the beginning where the inequality doesn't quite work out, but if we go far enough out, then it should. All right. And just another warning here, or comment rather. When we're investigating the convergence of an alternating series, so far this is really one of the only tests that we've seen that we can actually use to investigate whether an alternating series converges or diverges. Can't use the integral test, can't use any of those comparison tests, because those three tests all required positive terms. So an alternating series is going back and forth between positive and negative. So can't use those tests to help us with an alternating series. All right, so let's try an example. Let's look at example 1. So we're going to figure out if this series is convergent or divergent. And we see that we have this power of -1. Usually a good idea, usually helpful, to just rewrite this and separate off that power of -1. So kind of write it and then separate off everything else. And what we see here when we do that, we have our alternating component and then the term that we're going to call Bn for this alternating series. All right. So first step, we're going to state Bn. Well, Bn is all that stuff except for the alternating component. So it's the 1 over n term. And 1 over n, well, n is a positive integer, so this thing is positive. So Bn is always positive. All right. Second step, we're going to calculate the limit. So what limit do we calculate? We calculate the limit of just the Bn term as n goes to infinity. So let's fill in what we found for Bn. It's 1 over n. So we're doing the limit as n goes to infinity. And sometimes there's more work here. We're starting off kind of easy. This is just immediately a c over infinity form. So this goes to 0. And that's what we need. We need to show that that goes to 0. So it's a c over infinity form. Okay, so far so good. Now, we're going to prove the inequality. So for alternating series test, what's the inequality? Well, we want to prove that Bn plus 1 is less than or equal to Bn. This is what we want to prove. Bn plus 1 is less than or equal to Bn. So let's fill in, first of all, let's write in what Bn plus 1 is. So the way to interpret this, what is Bn plus 1? Well, we have Bn. This is the nth term, or the nth kind of non-alternating piece in our list. Bn plus 1 is just the very next term. So the way to figure this out is we look at our Bn formula, and wherever we see an n, we're just going to replace that with n plus 1. So we're going to end up with 1 over n plus 1. Okay, so we want to prove this inequality. So let's start by filling in what each of these terms are. Bn plus 1 is this fraction. And Bn is the fraction 1 over n. And we want to get this inequality to something that's obviously true. So if we cross multiply, so we'll multiply the 1 and the n together, 1 and the n plus 1. That's going to give us the inequality n is less than or equal to n plus 1. And yeah, I would say that's obviously true, because we have some number on the left, and then we have that exact same number on the right, but then we're adding a little bit extra. So this is definitely true. So, because this statement's true, it means that statement was true, which means what we wanted to prove was true. All right, so we're good. It's conclusion time. So conclusion, what's our conclusion? Well, this is a convergent series. And then we just want to state why. So what did we just do? We did the alternating series test. So we'll use the abbreviation, AST. All right. Let's try another one. Let's look at example 2. And, whoa, a little bit more going on here. So we've got the sum from n equals 1 to infinity, negative 1 raised to the n plus 1, times 2n squared over 5n squared minus 3. So again, helps to just kind of rewrite this. So kind of separate off all the pieces. So let's get that alternating component separated out of there. So we'll just write that negative 1 raised to the n plus 1. And it's n plus 1. That's fine. This is still going to do the job of alternation. So then what else do we got? 2n squared over 5n squared minus 3. Okay. So we've got the alternating piece, and then we've got the non-alternating piece. So step 1 for our series test here, we see that it's alternating. So we do see this alternating component, so we're thinking alternating series test. So first step is to state Bn. So Bn is equal to 2n squared over 5n squared minus 3. And just recognize, sometimes there's a little bit of work to do, that it's positive. Now, we do see a negative sign in the denominator here. So we do have to be a little careful. So if we check kind of the first one here, n equals 1, what happens? We get 5 minus 3, positive 2. And then once we get beyond that, this is just going to get a lot larger. So it's always going to be positive. So these terms are all positive. All right. So now we go on to do our limit. So what limit do we want to do? We want to calculate the limit of Bn as n goes to infinity. So let's fill in what we have for Bn. So it's the 2n squared over 5n squared minus 3 with n going to infinity. And let's calculate this. Now this one's a little bit more involved than the previous one, so we have to do more work. We see that this is a rational function. So we can use our common strategy, our x to the n method. And we just pick out the biggest power of n in the denominator and then just divide everything by it. So if we do that, we get 2n squared over n squared, 5n squared over n squared, minus 3 over n squared. Clean it up, simplify it down. So the fraction on the top becomes just 2. And then in the denominator, we end up with a 5 minus 3 over n squared. Okay. And this 3 over n squared, that's a c over infinity form. So that little fraction goes to 0. And what we see here is that this limit ends up being just 2 over 5. So 2 over 5 minus 0, just 2 over 5. All right, so we calculated the limit. We have an issue, though, because if we go back to our statement, boop, 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 we need the limit to be 0, and it's not. So that's no good. Alternating series test doesn't work here. So that's why, usually good idea, do the limit first, because if things are going to break down, usually that's where it's going to break down. All right, so alternating series test does not work. All right, so what are we going to do? Well, if you see that the limit doesn't equal 0, there's an immediate backup plan, and that's to use the test for divergence. So it's kind of nice. So if the limit doesn't equal 0, well, then the backup plan is that we have our test for divergence kind of hanging out in the back waiting for us, and we get to use it right away here. So what is the test for what do we have to calculate with the test for divergence? Well, we have to calculate the limit of the entire thing, not just the non-alternating component. So the limit, the test for divergence is the limit of an as n goes to infinity. So it's the limit of the entire thing. -1 raised to the n plus 1 with that non-alternating component. And we've looked at this before, these types of things before. So if the non-alternating component is not approaching 0, what happens is when we throw in this extra alternating component, some of the terms in this entire sequence are headed to positive. They're approaching positive 2 over 5. But then some of the other part of the terms are heading towards negative 2 over 5. So our sequence is kind of going in two different directions. It's kind of, well, it's diverging. So this limit does not exist. And because this limit does not exist, we say that our original series diverges by the test for divergence. So again, if we see that the limit here does not equal 0, well, what's happening when we throw that alternating component in, some of the terms are approaching positive 2 over 5, and then some of the terms are approaching negative 2 over 5. So it's like part of our sequence is going one way, part of our sequence is going somewhere else. So that limit does not exist. And because that limit does not exist, the series then diverges. All right, so we'll get a little more practice of this in class, so we'll see you then. Bye-bye.